Yeah, morning. My name's Richard Blewett from Withally Gold, and it's my privilege and pleasure to be the moderator for this next session. This is the big picture session, one of the highlights of our meeting. And we've got three awesome giants of the industry in Ross, Guillaume and Karen. And following each of their talks, we're going to have a Q&A session. And so I really encourage you to put your thinking caps on, be challenged by what our three speakers are going to tell us, and fire away and challenge them with your questions. Just a reminder to switch off your mobile phones or put them on silent. I'd also like to acknowledge the sponsors who make this meeting possible. The diamond sponsor here is Regis Resources, thank you very much. And our gold sponsors, Anglo Gold Ashanti, Newmont and Evolution Mining. Okay, so let's go. Our first speaker today will be Ross CAYLEY. He requires little introduction, I think, but he's going to talk about the giant Lachlan orocline in Eastern Australia. And I'm going to give you a 20-minute, a 22 and a 24.
Thanks, Richard. Let's get this show on the road. So what I'm going to talk about today is a long-term project that's still in write-up because it's got very big. And you're going to see a hint of how big it's got in this talk. You can't do this sort of work alone. We're a very small team in the Geological Survey Victoria, but we have benefited from awesome long-term collaborations, with the New South Wales Geological Survey and with Geoscience Australia, of course, and with a whole bunch of other players, and we just couldn't do this work without them and couldn't acknowledge them enough. And that's because we're talking about the eastern third of a whole continent. And, why is it a good place to play? Look, I'm just going to run you through a few basics just to remind you, it's a huge Paleozoic age fold belt system, and it hosts all these awesome deposits. World-class orogenic gold, world-class giant porphyry gold base metal systems, all sorts of awesome things are hosted in its geology. And the question is, a few questions. One is why, and the other is, are there more? And where might they be? And these are pertinent questions because well over half of this entire orogenic system is concealed below cover. And there's been limited success exploring under deep cover because it's hard to know where to go to look for things. And this might explain why. So in basic terms, in terms of how the system evolved, this is my take on how I think it evolved. I think it was relatively simple to start with. And this is important because it was relatively simple when lots of the major mineral systems were first formed. It started with the initiation of convergent margin activity along the east coast of Gondwana in the Cambrian, and that first cycle is a Delamerian orogenic event. And then when that system went extinct, it re-established further outboard as the Lachlan Macquarie Arc system, and then that migrated east through time to a position that's sort of now hidden underneath the Sydney Basin, and then it continued into the Permian, Carboniferous and Permian, as a New England system that Gideon's going to talk about next. And of course it continues today in places like New Zealand. This is what the talk's going to be about. There's a lot to cover in here, but it's really, in summary, you'll see as I step through, it's about building a logical pattern for why we had to do what we did, what the constraints on this are, and then what the implications are. So let's start with a toolkit for trying to understand this complicated package of rocks, and that's geological systems analysis. So everybody's familiar with the subduction accretion system. Most people agree that these systems were operating in the Tasmanides throughout the early Paleozoic, and they're responsible for building most of the geological elements preserved in there today, and the mineral systems are related to that. Now, what's important about understanding this system is there's all these different elements in the system which we all recognise, but they're really diagnostic. And those diagnostic characteristics are preserved in the rock records. Obviously, there's the arc. People recognise arc volcanics. When we have an arc, you often have a back arc system. And it's got some diagnostic characteristics. It's often got magmatism that accompanies sedimentation in a marine environment with distinctive chemistry. And on the other side of an arc, you've often got an accretionary wedge where material's being off-scraped from the downgoing slab and it's piling up and forming a new sort of orogenic belt in front of the arc. And that's often characterised by no magmatism, lots of sedimentation and thin depositional deformation, quite different to a back arc, for example. And then outside these systems, we've got bits of the crust that haven't got to the system yet. And if they get preserved that way, they have their own characteristics, like no deformation at all, perhaps nothing much has happened and not much magmatism either, and that they happen on both sides, the continent side and the ocean side. So I'm showing you these with colour-coded signs because I'm going to come back to this later. We use this sort of logic to try and unpack what's happened in the Tasmanides where it's got complicated. Often it's shown as a 3D model, but essentially it's just a cross-section with extra depth added. So there's competing models for understanding the Tasmanides, and that's made it complicated for explorers. Which one do you go for? These things are important for understanding mineral systems. So I'm going to have a bit of a Victorian bias here because there's some interesting things happening in Victoria. And one of them was a breakthrough model that was proposed in the mid-90s by David Gray and David Foster, the double or triple divergent subduction model. And that was designed to explain the opposing observation of the opposing geometry of various systems of similar age Ordovician deep marine rocks that they interpreted had all been deformed in accretionary systems. And how do you explain all these different vergences, the eastward vergence and westward vergence? Well, you just put a few different simultaneous subduction zones in and hey presto, you've got it explained. And it was a really insightful model that explained a lot of things. Now, I'm aware there's lots of other models as well, including New South Wales-centric ones. I'm not really going to touch on them in too much detail, but you'll see what I think about them as we go through the talk. So getting back to Dave Gray's model, we thought a lot about this model. So these are the areas that they thought were Ordovician and Cambrian accretionary systems active through the Ordovician. And in the eastern Lachlan, certainly, this makes a lot of sense. There's places like Narooma with broken formation and maybe even a preserved bit of subduction trench there. And we can see the same patterns in the Tabaraba zone and the Malakuta zone in Victoria. And nearby, there's these Ordovician andesitic arc-type rocks, which are the same age as the accretionary deformation that's been dated using Ogon data. This all makes sense. When you go to Western Victoria, the Western Lachlan, it starts to get a bit trickier. So when you look at the same age rocks in the Bendigo zone, it's a layer cake of Ordovician turbidites. There's no evidence of syn sedimentary deposition. It looks quite different. And so we don't think that really looks like an accretion wedge at that time. That's what we thought. And we also thought that the adjacent Melbourne zone didn't look like that either because it's a really well-defined layer cake full of fossils and it didn't actually suffer any Ordovician deformation at all. It didn't suffer deformation until the end of the Silurian. The Stawell zone does look like an accretionary wedge, but it's been dated now, it's too old. It's part of the Delamerian system, it's Cambrian, so it's not part of this model. When you think about the Omeo zone, which was interpreted as an arc in this model, when you look at the Omeo zone, it's equivalent to the Wagga zone, and overall the characteristics of that look like a back arc basin, not like an arc. So we think that looks like a back arc basin. So in summary, these systems work quite well, but they're not perfect. They don't work that well. So there's more room for improvement. So we were keen to follow that through. So an example of it not working perfectly is once you recognise the Omeo zone looks like a back arc, you've got this problem where you've got a back arc juxtaposed against an accretionary wedge with no arc in between. This does not happen in nature. There's always an arc in between. So it's telling us that in this system in Victoria, there's been a lot of modification since this system was active as a subduction accretion system. And how do you resolve that complexity? Now, we think we might be able to resolve it here because there's a great big strike slip fault separating these two things, and it's well exposed in the Victorian Alps. It's the Kiwi Shear Zone. It's a 5 kilometre wide dextral ultramyelinite zone, subvertically dipping, very significant structure, but what does it do? So let's step on. So how do we constrain these things? We've got these observations, what do we do with them? So paleogeography is a really cool tool. So this is where the Kiwi Shear Zone is. So that can juxtapose a couple of zones and maybe it's done something, but what has it done? So west of that, part of what was thought to be contiguous Victorian geology, Chris Ferguson years ago did some good work in the southern Tabaraba zone, looking at Ordovician turbidites and paleocurrent directions. And you can see there, it all comes from the west in the Ordovician. So we're going, okay, cool, what's happening upstream of those paleocurrents at that exact same time in the adjacent Melbourne zone? So what we have there is deep marine pelagic black shale and chert. So what that tells you is that those turbidites in the Ordovician cannot have come from the source area that's next door to them now because they're not there and it's all black shale anyway, so they didn't move through there. So there's a great big break between those two adjacent areas. They cannot have been juxtaposed at the time this was happening in the Ordovician. There's a break there. So this is the motivation for the model that was proposed in the Tasman File Belt and Victoria volume in 2000 by the Geological Survey. So what we did is we just took Eastern Victoria and stuffed it north on a transform fault, which we couldn't really see anymore, to explain the paleogeography. And in the course of doing that, we had to move most of New South Wales, but hey, it's not our state, so we didn't care. And And then we looked at it, and what we saw was we had east verging thrust in the Bendigo zone, the same age in the long strike from west verging thrust in the Tabaraba zone. What the hell happens there? Who cares? We didn't worry about it. We couldn't fix that problem. Meanwhile, the other model is the double divergence subduction model, and it kind of doesn't work either for the same reason. They've got paleocurrents coming off Gondwana, then there's none in the Melbourne zone, and then there's a whole bunch of them in the eastern Lachlan coming from the same direction. How does this work? That model doesn't work either. Also, it doesn't actually predict gold, so it's not very useful. So, for example, the Malakuta eastern subduction zone, no gold at all. The western one, world-class gold, and the middle one, a little bit of gold. So it's not really helpful for helping explorers do what they want to do best. So we want to do something better. So we need to look back at more fundamental constraints. And one of those is understanding the orogenic events that have tied all this region together. So here's a time-space plot. The details are not important, but it's sort of south and west at the left-hand side, and north and east in the east-hand side. And it just shows a general progression from old in the west and younger in the east. And that's marked by the orogenic events and where they go. So that's where, in the Cambrian, end of the Cambrian, that's the Delamerian orogeny there, terminating deformation in the Adelaide fold belt and in western Victoria and in western New South Wales as well. You can see little bits of it popping up in the Thomson fold belt. That's the Anarchy inlier in there to the east. Then there's this very widespread event, which is the Bonanvin orogeny, and that occurs after and terminates Macquarie Arc activity in eastern Australia. And you can see little bits of it turning up in far north Queensland. And then there's some other events. The Bindian orogeny confined mostly to the eastern Lachlan fold belt, and then the Tabaraban orogeny, which is kind of everywhere. And by this stage, we're confident the whole system is together as a united system. Now, what I want to focus on now is places where these orogenic vents aren't, because there's lots of detail to be gained from looking at those. And one of those classic places is the Bendigo zone, right next, just the first zone east of the Delamerian fold belt. So the thing about the Bendigo zone is it's got plenty of Cambrian rocks, including rocks that are older than the Delamerian orogeny, but it hasn't got any Delamerian orogeny, and we can demonstrate that, we can prove it. So here's some really good mapping Frans Vandenberg did back in the day in central Victoria, eastern edge of the Bendigo zone. We can see the lower parts of the crust exposed in a big fault. And it's well exposed. These are early Cambrian tholeiitic basalts, Morb. There's fossils, trilobites in interflow sediments. These things are early Cambrian. We're very confident about that. There's submarine, there's pileobasalts in them. They're conformably overlain by pelagic chert. So this is deep marine, miles from a continent, stuck out there somewhere. And then there's a shale on top of that that's also conformable. And then in this creek, there's a transition where you can see the very first turbidite arrive, and that very first turbidite is early Ordovician. So this sequence, which is really well exposed, straddles across where the Delamerian orogeny should be, but there's no Delamerian orogeny there. So what that means is there's a gap. And this is not quite what here we go, yes, right, so my computer slowed down, sorry about that. So what you can see there in the blue arrows is the areas in Victoria where we can demonstrate there's no Delamerian orogeny. So we've got early crust and it just goes right through with no hint of Delamerian. This is a separate orogenic system outboard, and the Macquarie Arc is part of that system. This is important. Let's move on to the next step. Okay, so in order to take this understanding further, you really need to use geophysics, so that's the next step to do. So we're all familiar with Eastern Australia and what happens when you do geophysics with it. It's just this fantastic way of overcoming the tyranny of cover and seeing what's underneath. And the first thing that's obvious in that data to me, apart from how awesome it looks, is that you can see that Western Tasmania is connected to Victoria, central Victoria. This was an unexpected result at the time. And this is where the idea for the Selwyn block under central Victoria came from. You can just see this connectivity in the magnetics going straight underneath from Western Tassie through King Island and up underneath Melbourne and up underneath central Victoria and the Melbourne zone. So without having outcrop, this would have just been where the story ended, but fortunately we do have outcrops of this stuff, and they're shown in the red dots. And that includes rocks that are co-over with and have the same chemistry as the Mount Reid volcanics in Western Tasmania and the Dundas Trough, and that's the Jamison volcanics, and there's mineral systems in there as well which are being explored right now. There's one really particularly good outcrop that showcases our understanding of what's going on here. And this is what happens when you have the Delamerian orogeny in the Lachlan fold belt. So we have got these amphibolite grade polydeformed gabbros, metagabbros, and they've got recumbent folds in them and a bunch of other stuff. And then there's a really prominent unconformity, and above that, there's fluvial quartz cobbles coming off a continental source, sitting in cherts, conformably overlain by a limestone that's got earlier Ordovician trilobites in it. So this tells you that deformation in the underlying rocks is older than the earliest Ordovician. It's Delamerian, it's Tyanan. So this is the Tyanan orogeny in central Victoria. So that sits in here. So it's east of the Bendigo zone. And we can demonstrate the relationship with that was established in the Ordovician. It's a little bit of the Delamerian sitting in the middle of the Lachlan, surrounded by all these areas where there isn't Delamerian deformation, and you can demonstrate it. So there's something very strange going on here. It's like a little microcontinent embedded in the middle of this oceanic system. So in this model, it just sort of sits in the middle of this bit. That's where a microcontinent sits. You can straight away see the implications it's going to have for the simplicity of this model. So we needed to have real confidence about this, so we shot some seismic to test it in 2006. And that's where the seismic line is, and it's great data. I'm not going to talk about it too much, but you can see there's the whole line all strung out, all 600 kilometres of it. And what you can see there is a bunch of stuff underneath the Bendigo and the Stawell zones. It's imbricated oceanic crust. I think it's probably an important source for the orogenic gold. All mushed up, consistent with all the faults and folds you can see in the rocks at surface. And that's got a completely different seismic character to what's sitting underneath the Melbourne zone, which is this much more simple, laterally extensive, multi-layered package of rocks. And we think that's the Selwyn block sitting under there. It looks completely different. If it was all accretionary, it should look the same. It doesn't. So that's what's driven our interpretations. And we think this is important for understanding things like world-class gold in the Bendigo zone, but also the Melbourne zone. We've got this potential gold reservoir down in the middle and lower crust. We've got plumbing systems that have tapped into it and can direct gold up to where the world-class goldfields we know exist, and potentially linking systems into places like the Western Melbourne zone. And we can repeat that on the eastern side of the system as well. We can see things like Woos Point, Walhalla Goldfield coming through the east there. So this is our framework model for understanding orogenic gold, but it's got much bigger implications than that for the Tasmanides. Stepping up to the north, this data I've shown you here was taken before New South Wales stepped up and did some really good high quality aeromagnetic data over the Murray Basin. And that's what this data is here. This is a revolutionary data set because it demonstrates all these cool things happening, which we can project from where these rocks are exposed in Victoria into New South Wales with confidence. So, for example, the Cambrian accretionary wedge off the Stawell zone tracks up to the Murray and then it swings east and runs out into central New South Wales undercover. You can see it in the magnetics, it's dead clear. And then it's truncated by this north-south trending thing, and we know what that is because we can map it in Victoria. It's the Kiwi shear zone. And then the northern end of that is truncated by the southern margin of the Thomson Fold Belt. There's a lot of really weird, interesting, fundamental things going on in here. Because we've got that control in Victoria about the character of these packages and also the age of the faults that separate them, we can take that understanding and just extend it into New South Wales, test it against local controls. It's stacked up pretty well. So we've colour-coded the faults with their age, we've colour-coded the zones with their affinity, and we can just fill in the blanks because we've got that exposure in the southern part of the Great Divide, and we've just colour-coded it. So Ordovician is in blue, the arc rocks are in orange, the high temperature metamorphic Silurian are in green, etc. So this is giving us a fundamental framework for a large part of southeastern Australia with all those basins removed. We've got our paleogeographic discontinuity that we've still got to deal with, and that's in here. And this is one we know about from the paleocurrent data. And what this new magnetic data immediately showed us was this is wrong. It does not go through there, but we still have to explain. So that kills the model, but we still have to explain this bit somehow. So thinking hats on, time for something different. We've got this other big new strike slip fault though we have mapped, that's the Kiwi shear zone, and it's a big fault where it's exposed in Victoria. We can see it in residual data from the passive seismic array. It's a depth persistent change in velocity, goes down through the whole lithosphere, and the position of that offset doesn't change from the surface position of the fault, which is marked in red. This is telling you this is a lithospheric scale vertical structure. It's huge. In legacy New South Wales data, you can see this thing. So I've had a look at some of this legacy data and I reckon I can see it in there. So that's where the fault's been mapped. That's the Booth-Uganda fault in New South Wales. There's a seismic line shot over it. There's the data. So that's where the fault plots surface there on the magnetic data and the mapping. So I'll just zoom in a bit. I reckon I can see it there. I reckon it's vertical. So this wasn't in the original interpretation because people weren't looking for vertical structures in seismic data. And you can't see the actual structure. You can just see the change in character on the other side. But that's what we reckon it is. We reckon it's dextral. And these sorts of faults, these are the sorts of faults that can explain these sorts of juxtapositions. They're really big structures. But how would that happen? So with these constraints, we can start looking at our geological modelling and start trying to unpack some of this stuff and apply it to this new cover stripped off Silurian map of southeastern Australia. And we can do it by comparing the order in which these things occur, these characteristic bits of this system, depending on the configuration of the subduction zone. So for example, let's put a cross section through here and map out all the different bits and pieces in terms of what we can see. So we can see bits of back arc, bits of arc, and bits of accretionary wedge, and then you can apply to interpretation to it. It looks like a continental dipping system to me, but with a couple of extra bits of continental dipping system thrown in. But we know there's strike-slip faults there. What it doesn't look like is an ocean dipping subduction system. It just doesn't match. The accretionary wedge is on the wrong side, so I reckon we can just kill that. It just doesn't, the Wagga zone doesn't look like an accretionary wedge. Let's have a look at a Victorian one. Same sort of deal. We end up with a pattern of things, and we can just pick bits out of that pattern. So bits of it look continental dipping. Bits of it can't occur in nature, but that's where these big strike faults are. Bits of it potentially look ocean dipping as well. Plus we've also got a microcontinental block thrown in there. So in summary, Eastern Australia, it's all screwed up. You know, it's different. Wherever you look, it looks different. So we've got all these crazy things happening. How do you make sense of this? It's just really hard to make sense of. Until, fortunately, we've got a key exposure in Victoria which let it happen. Something that could explain this complexity. So because it's all screwed up, it's not like a textbook system. So a textbook system is just exactly what I said. It's like a 2D cross-section extended forever. So you just understand one bit, you can understand all of it. And to that end, it looks a little bit like a warehouse. You understand one bit of a warehouse, you can understand all of it. But what our warehouse looks like is this. So how do you make sense of it? Well, one way of making sense of it, okay, so this is a Russian vodka warehouse. That probably explains what's about to happen. So the reason I'm showing you this is to indicate how quickly something that's been stable for a long time can suddenly change to something that looks really, really different. And the difference is an appreciation of what happens if you've got a collider and how quickly it can cause change. And we think we have a collider. We think it's Tasmania and a Selwyn block stuck in the middle of this system. And it's here. So here's a numerical model that Louis Moresi did in Underworld at the same time that I was doing this work independently based on the geology, and he showed how it works. The collider was in orange. It collides into a simple system, and it causes a slab to slow down and change, and the uncongested part keeps running, but now it can't advance, so instead it wraps around the collider and causes a lot of complexity. So what does this mean? Yep. What does this mean? It means that you can have collision along strike from extension. Okay, right, so just keep rushing it. So if you've got collision and extension, you need strike-slip faults to accommodate it. When you have extension, you get rifting, and what it really shows is once linear things become really highly convoluted and confusing. And we can see all these patterns in southeastern Australia. We've got strike-slip faults, we've got rifts which are the same age as the strike-slip faults, and we've got lots of these highly curved things, and we've got evidence, independent evidence that duplication of things like Macquarie Arc might be possible and explain some important things. Like Gordon Packham's really insightful work. We've got ideas about subduction and LFB evolution related to phases of rollback, and we've got evidence that rollback and extension is linked to sedimentation. Things like Chris Ferguson's work. So when you apply that to this system, and we've got a structural template that's constant throughout, you can unpack it through time and start to reassemble things. So we think that's what it looked like in the Ordovician when the mineral systems were formed. It was simple. It's all arranged in a continental dipping subduction zone system. It's essentially the warehouse and reassembled. It explains things like why the Western Lachlan in Victoria's got a lot of gold, because it's not part of this subduction system. It's instead sandwiched between the Collider and Gondwana. It's actually still got a source rock for lots of gold. We've modelled it. How far north does that gold go? Oh, that's an interesting question. Today it's all folded, and we're testing that in Victoria, but it's relevant for New South Wales as well. It's an alternative way of thinking about previous models, because it's got that change in vergence at a regional scale. It's the same as Dave Gray's model, just using one subduction system folded, not 3 subduction zones. In terms of mineral systems, it's really important because really key things like Cadia, Parkes, Lake Cowell, probably all developed along strike, and now they're all in different places, and that fertile zone is spread all over the place, and half of it's buried. And this is a toolkit that can be extended north into Queensland, in the Thomson Fold Belt, which I was going to try and talk about, but I didn't make it, and south into Tasmania as well, so I'll leave the talk there.